This week we are studying ocean currents, and that is directly related to how salty the ocean is. So the first thing we need to look at, these are the questions you looked at yesterday in the textbook. I know you did not have a lot of time to do it, but let's take a look at what causes currents. First of all, we're going to look at ocean water chemistry, which just means what chemicals, what makes up ocean water. We've all gotten a mouthful of ocean water. It's very salty, but other people have mentioned it also tastes, somebody said it tastes like fish. It's got lots of algae, it's got lots of other things in it. But if you look at this, salinity is just another way of saying saltiness. Salinity is how much salt is in each kilogram or liter of water. Metric is very nice because 1 liter of water weighs 1 kilogram. Very convenient. And there are 35 grams of salt in 1,000 grams of water. And I showed you that in our little demonstration, how much 35 grams of salt looks like. And it's really quite a bit of salt. Now, of course, in the ocean, it is not just salt. It is some other chemicals as well. Table salt is sodium chloride, a 1-to-1 ratio of sodium chloride. So sodium is Na, chloride is Cl. Now you notice these numbers here. There is 30% of the salts are sodium and 55 are chloride. Well, if sodium and chloride match together 1-to-1, then only 31% of this chloride is with the sodium. Does that make sense? So 1/3, 31%, of the salt in ocean water is sodium chloride. So that leaves, what's 55 minus 31? It does not depend. Who said it depends? How about 24? So 24% of that chloride is bonded together with something else. Well, it turns out magnesium chloride, calcium chloride, potassium chloride, if you look at the periodic table, these things all bond and make other types of salt. Magnesium chloride, for instance, MgCl. Magnesium chloride, or mag chloride, is what they put on the roads to melt the snow and the ice. And they do this because I believe it's a little bit less corrosive than the sodium chloride for rusting your cars. And also they can put it in a liquid and they spray it on the roads before it snows. And so there's a little bit different properties. So there are many different salts that make up the ocean water. So if you just took table salt and mixed it in, not quite ocean water. All right, so we're going to talk in a minute about what else affects that. But so ocean water, 96.5% water, and then 3.5% salts. And if you see this, 35 grams per 1,000 grams, you do the math there, that's 3.5%. What you need to know from this, basically, is that the ocean water is salty, but it is not just table salt, it's other types of salts. And more important than this really is what's causing differences in the salinity. Okay? Other things that affect the ocean water, we've talked about this a little bit, the temperature, which is affected by the sunlight. Gases dissolved. What kind of gases would be dissolved in the water? No, like air gases, right? This oxygen, right? The main gas that's going to be dissolved in water is oxygen, right? The fish need the oxygen. Fish, marine creatures, they get the oxygen out of the water with their gills the same way we get oxygen out of the air with our lungs. And so the dissolved oxygen is also affected by the temperature. And you can imagine there's going to be more light and a higher temperature near the surface. Similarly, with the gases dissolved, if there's more mixing, you're going to get more bubbles of water, more oxygen. Okay? And all that, of course, affects density. So let's look at our next page. Oh, this is from the textbook. We're not going to spend a lot of time on this, but this is just looking. You guys know that when people go diving, there's a lot of pressure, a tremendous amount of pressure. You know, water is heavy, right? A gallon of water weighs, what, 8 pounds? So water is very heavy, and it does not compress. You can't squeeze it. And so the deeper you go in the water, the more water there is pressing on you. So it's actually very difficult. Submarines, if they get too deep, will actually be crushed by the weight of the water. And same thing with humans. Animals that live that deep have special adaptations. But if you look at this, the ocean is divided into different zones based on these things. This, I know it's hard to read, it's from the textbook. This is called the surface zone, obviously up at the surface. And here you're getting the effects of light. It's going to be much warmer. This is going to be the warmest part of the world, of the ocean. And then transition zone, deep zone. And again, as you get deeper, you have much less light filtering down because the light just can't go through all of that. Temperature is going to get colder as you go down. The pressure increases, the saltiness increases, the density increases. So you can see these things, this red arrow pointing this way is telling you that the pressure, the density, the salinity or the saltiness, those things all increase as you go lower. The temperature is all obviously warmer when you're higher up. So pretty much logical sort of things, but this is going to affect the currents. All right, let's move over. So here we have currents are basically rivers of water in the ocean. And just like with a river, they can be used for transportation. So rivers of water within the ocean. And as we talked about in our Do It Now, it's pretty easy if you just look at a picture of the Earth to say, well, obviously, it's colder near the poles and it is warmer near the equator. And so that temperature is going to be one big effect of what's affecting the density, which will affect the currents. The surface currents, again, down to several hundred meters, caused by winds and the spinning of the Earth. We were talking about the Gulf Stream, which is here, and as you guys suggested, it's taking the warmer water up further north. And then the colder water comes this way. So I don't care if you know all of the currents, but you should know what's causing them, the density and the saltiness. And as we look at our lab tomorrow, we will demonstrate the saltier, colder water being more dense and see some examples of that causing currents. All right? Again, as they mentioned yesterday, because the Earth is turning, that makes these, instead of going straight up, it makes them curve a little bit. And in the northern hemisphere, they go clockwise, and in the southern hemisphere, they go counterclockwise. And that is called the Coriolis effect. It affects winds, but because the Earth turns, it makes circular patterns, which, you think about it, is useful for getting places. Questions about that? Okay, and here, showing the deep currents, going back just a second here, this one is primarily the surface currents caused by the winds and the Coriolis effect. And they're very predictable. The prevailing winds are predictable and don't change a lot. So then the deep currents, obviously they go deeper than several hundred meters. They stir up the oceans, and they're caused by differences in density, temperature, and saltiness, salinity. So density is going to be affected by these things. Now, we talked about this and we did a little demonstration. If it's colder, if it's saltier, it will be more dense. If it is colder, the molecules are closer together. If it is saltier, it's water plus other things in the same volume. So if you have evaporation of water, that will make it saltier. If you have freezing, only the ice freezes, leaving the salt in the water. Warmer water, the molecules are moving faster, they're farther apart. If it's less salty, it's less dense. And of course, the sun warms up areas and it evaporates. So here's basically what you're getting. This would be very simple, as we mentioned last week, the waves and the currents. If there were no continents, it would just be a big circle. But of course, the continents deflect them and make them go different directions. But here you can see at the equator, the sun shines on the water, it gets warmer, and so it becomes less dense, heats up, and it rises. And at the poles, and you do have some evaporation, which making it a little bit saltier. At the poles, of course, it's colder, and the ice freezing makes it saltier, and so that makes it denser and it sinks. And because it's falling here and rising here, the differences in pressure are causing the current. And again, we talked about this as being the global conveyor belt. It will ultimately, over really thousands of years, all of the water in the earth gets mixed. Now, why do you care? Why does it matter that the ocean water mixes? Well, there's something actually really interesting about the ocean water mixing. Oh, there's one other thing here, too. Water is this very interesting thing. Usually when something becomes solid, it's more dense and it sinks, right? Solid things sink in liquids. But what do we call solid water? Ice. Does it sink or float? It floats, which is another really weird thing, because the water will be most dense at 4 degrees Celsius, and then it freezes at 0 degrees Celsius. See, look at that nice metric scale. And then when it freezes, it becomes ice and floats. And so even in lakes, you're going to get this circulation. And one of the things this does is stirs up nutrients, it stirs up water. Imagine if lakes and ponds froze from the bottom up. What would happen to the fish? Yeah, they'd be up on top. So as the water froze, the fish would be shallower and shallower and shallower. And also you couldn't go ice skating. No ice hockey. It would be so sad. But it's a really odd thing about water, but it also allows living things to live in ponds and lakes all year round because it freezes on the top and it's still cold, but not frozen below. Okay, strange things about water. Yes, hang on one moment. So in the oceans, we see this same effect. And in fact, once again, in the oceans, the density currents cause something called upwelling, but this is incredibly important for marine life, for ocean life. And so what you're having here, and this is something, it was in the end of your questions, it's called upwelling, which is a little bit of a strange word, but again, once you think about it, it makes sense. And upwelling, cold water is being pushed up from the deep ocean. It brings a new supply of nutrients. So all the plankton, all the algae, all that little stuff that's stirred up is coming up for the bigger fish to eat. And so this says nutrients feed enormous schools of fish, such as these anchovies. Yum. So again, the reason the cold water is coming up, because that seems strange. Why would cold water go up? Well, here's warm water. The water's shallower. Right? So it's shallower, so it's heating up, so it's less dense. And then this is coming here. You've got wind moving it this way. And so you get this big current. But once again, the currents, not only are they helpful for transportation, not only are they helpful for mixing the oceans, but this allows life to thrive in areas like this. And then, of course, the fisherman obviously knows where to go to get that. Okay, so that is our oceans and currents for today. Yes. Okay. Chapter 13.